Now, how to determine the charge to mass ratio of electron or cathode rays? For this, Thomson made an extensive experiments on this discharge tube. So let us see experiments on this Jj Thomson model. Jj Thomson was able to measure the ratio of the electrical charge to mass of the electron using the cathode ray discharge tube. For this, he applied electrical and magnetic fields perpendicular to each other as well as the path of the electrons. So the experimental setup of Jj Thomson to find out the charge to mass ratio is shown here. Look at this. This is the cathode and this is the anode, and these two terminals are connected to a high energy source or high voltage source. The cathode, when a high voltage is applied to this, cathode rays are originated from the cathode. So therefore they travel from the cathode towards the anode. So look at this path. This is the path of the cathode rays. So therefore they are traveling from this. During this path, suppose this is the path of the cathode rays. These particles should strike at the point B. Look at this point B. In absence of electric and magnetic fields. Here we are not placing any external electric or magnetic fields. So therefore, in absence of these two fields, the cathode rays should fall at point B. Suppose when the magnetic field alone is kept, here look at the magnetic field. This is the magnetic field which contains north and south poles. When the magnetic field alone is turned on, electrons strikes at the point C. Look at this point C. Yes, this is the point C. So that means in presence of magnetic field, the cathode rays should strike at C. Similarly, when the electric field alone is turned on, the electron strikes at point A. So this is the three cases A, B and C. When both magnetic and electric fields are off or when they are balanced so as to cancel each other's effect, the electron once again strikes at point B. Look at this. Here electric field and magnetic field cancels each other. Once again the cathode rays should strike at the point B. Now the observations drawn by Jj Thomson from this experiment is the amount of deviation of the particles from their path in the presence of electric and magnetic field is depends on the following three factors. The first one is the magnitude of negative charge on the particle is greater the magnitude of the charge on the particle, greater is the interaction with the electric or magnetic fields, and thus greater is the deflection. So this is the first important observation made by Jj Thomson. And coming to the next one, lighter the mass of the particle, greater the deflection. So that means when the particle is having less mass, it is getting more deflected. Third one is the deflection of the particle from its original path increases with the increase in the voltage across the electrodes or the strength of the magnetic field. So to understand this, let us go to this following animation. So here when the applied voltage is increasing, the deflection of the particle from its original path, this is the original path, from its original path is deflected. So these are the important observations made by Jj Thomson. Based on this experiment, Jj Thomson determined the value of charge to mass ratio. This is also known as specific charge, which is E by M. So here E by ME is equal to 0.755880 into 10 power 11 coulombs per kg. So this is the specific charge of the cathode rays, or cathode rays consists of the stream of particles, those are called electrons. Hence this is the specific charge of the electron. Here ME is the mass of the electron which is expressed in kgs, and E is magnitude of the charge on the electron in coulombs. That means for this Jj Thomson, he does not know about the charge of the electron. So but he found the ratio of charge to mass. He found that the value is this one. So this is about the Jj Thomson experiment on discharge tube. Later, the charge of the electron was found by Mulliken by his Mulliken oil drop experiment. Let us know about the Mulligan oil drop experiment. The discovery of charge of an electron was later given by Mulligan in 1898 by his experiment. In this experiment, he taken some fine oil droplets which are allowed to spread in the chamber using an atomizer. The air in the chamber is subjected to ionization by X-rays. Let us see the experimental arrangement of Mulligan oil drop experiment. Look at this. This is the schematic representation of the apparatus used by Mulligan. So this chamber, at the right hand side we have atomizer. This is the atomizer. The purpose of this atomizer is to produce oil droplets, fine droplets of oil which can be produced from this atomizer. And this chamber consists of two plates. This is the positive plate and this is negative plate. Now the movement of the droplets was viewed with the help of a microscope which is at the right hand side. Look at this. This is the microscope. These plates are connected to a high energy source. So therefore these are electrically charged plates. Now some fine oil droplets were allowed to spread into the chamber by this atomizer. Look at this. Oil drops are coming from this atomizer on the upper chamber. These oil droplets were subjected to ionization by the X-rays. Therefore, using this X-rays, they are getting ionized. Now, because of the ionization, they produce electrons. The electrons produced by the ionization by the air attach themselves to the oil drops. These are attached to the oil drops. Look at the attachment of the electrons to the oil drops. When sufficient amount of electric charge is applied, which can just balances the gravitational force acting on the drop remains suspended in the air. So look at this. When the sufficient electric charge is maintained between these two plates, when the electric charge is varied, the position of the droplets is also varied. So therefore, for a definite electric potential or the voltage, the drops should remain. So that means at this stage, the gravitational force is exactly balanced by the applied voltage. So this is the experiment made. So therefore, these electrons will be adhered to the oil droplets. From this experiment, Mulligan observed that smallest charge found on them were approximately 1.59 into 10 power minus 19 coulombs. Later, these oil drops were further analyzed and the smallest charge which is accumulated on this oil drop is 1.59 into 10 power minus 19 coulombs. And the charge on each drop was always an integral multiple of this value. So therefore, an oil drop contains an integral multiples of this 1.59 into 10 power minus 19 coulombs as the charge. So therefore, on this basis, he concluded that 1.59 into 10 power minus 19 coulomb is the smallest possible charge and considered this as the charge of the electron. So this is the Mulligan oil drop experiment. So what is the purpose of this Mulligan oil drop experiment? The purpose of Mulligan oil drop experiment is to find the charge of the electron. What is the charge? The charge of the electron is 1.59. Generally we take the approximate value, that is 1.6 into 10 power minus 19 coulombs is the charge of the electron. Before, the Jj Thomson, he found the charge to mass ratio of the electron. Later, using the Mulligan oil drop method, we have found out the charge of the electron from these two values. The mass of the electron is found as 9.1 into 10 power minus 31 kgs. And suppose if we express this in AMU, the mass of the electron is equal to 0.00055 AMU. Its charge was determined by Mulligan by his oil drop experiment as 1.6 into 10 power minus 19 coulombs. Otherwise, if it is expressed in electrostatic units, it is minus 4.8 into 10 power minus 10 electrostatic units. That is called ESU. Thomson gave the E by M ratio, that is the specific charge ratio for an electron, and its value is 1.76, which is approximated as 1.76 into 10 power 8 coulombs per gram, or which is 5.27 into 10 power 17 ESUs per gram. And also the density of the electron is, the density means it is the ratio between the mass to volume. So therefore, the density of the electron is 2.17 into 10 power 17 grams per cc. So these are the properties of electrons. A similar type of experiments is followed by different scientists. Later, they also concluded that in addition to the electrons, there are some particles which are called protons which are associated in matter. So let us know the another fundamental particle that is called protons. Let us go to the discovery of protons. The presence of positively charged particles in an atom has been predicted by Goldstein based on electrical neutrality of an atom. Dear students, you know atoms contains electrons. These electrons are carrying a negative charge. So that means in order to maintain the electrical neutrality, they must contain some positively charged species. These positively charged species are known as protons. The discovery of proton by Goldstein was done on the basis of the cathode ray experiment conducted by using a perforated cathode. So here Goldstein repeated the same experiments by using a perforated cathode. Look at the experimental setup of the cathode rays which was used by Goldstein. Yes, this is the discharge tube and this is the anode and this is the cathode, and these two are connected to a high voltage source. Here we have taken a perforated cathode. Instead of a single metal sheet, we have taken perforated. That means it contains small holes. Look at this. These are the holes. So therefore, when a high voltage is applied to this, here from the anode, it gives some particles. This stream of particles is called anode rays because these are originated from the anode. So look at the origination of the anode rays. Look at this. Here these particles are traveling from anode, and here because of the perforation in the cathode, they are passing through the cathode. Look at this. These particles are traveling from this, and these particles which are coming from the anode are called, these are having a positively charged, so therefore these are called anode rays. Just like cathode rays, some rays were found to be coming from an anode. These rays are called anode rays. These are also known as canal rays. Anode rays were found as a stream of positively charged particles in contrast to the cathode rays. A cathode rays consists of a stream of negatively charged, so therefore cathode rays are negatively charged rays, whereas these anode rays are positively charged rays. So here, when a hydrogen gas is taken in the discharge tube, these positive charged particles were found to be the protons. This is the discovery of the anode rays. From this, we can go to the properties of anode rays. Anode rays travel in straight line, and these are material particles. These anode rays are positively charged and get deflected by external magnetic field and affects the photographic plate. The E by M value of these rays is smaller than that of electron. The E by M value of anode rays depends on the nature of the gas. So previously, in case of the cathode rays, the E by M value is independent of the nature of the gas. But here, in contrast to the cathode rays, the E by M value of the anode rays depends on the nature of the gas. That is the difference between the cathode and anode rays. Another one is E by M value of anode rays is maximum when the gas present in the tube is hydrogen. By the dissociation and ionization of hydrogen under low pressure, discovered with the charge +1 and mass +1, particles are called protons. So these are the properties of anode rays. So these anode rays consist of positively charged species. These positively charged species are called protons. Let us go to the properties of the proton. So the charge on proton is plus 1.6 into 10 power minus 19, or when it is expressed in electrostatic units, it is 4.8 into 10 power minus 10 ESU. Coming to the mass of the proton is 1.673 into 10 power minus 27 kgs. Suppose if it expressed in AMU, it is 1.0072 AMU. The E by M ratio proton is 9.5 into 10 power 4 coulombs per gram, which is having a less magnitude than electron. So this is the discovery of the second fundamental particle called proton. Later experiments shows that in addition to these two fundamental particles, another particle that is called neutron, which is also incorporated in atom. So let us know the discovery of neutron. The discovery of neutron was given by Bothe and Becker. Bothe and Becker reported that if certain light elements, say for example beryllium and boron, were exposed to X-rays, a very high penetrating radiations were obtained. The nature of this radiation was established by James Chadwick, and who showed that they consisted of mass nearly equal to proton with no net charge, and these particles were called as neutrons. So from this experiment, light elements were also contained. These particles are originated from the atom itself only. That means atom contains these particles. What are the particles associated in the atom? Electron, proton and neutron. All these particles are associated in the atom. Now let us go to the properties of the neutron. So here neutron was discovered by Chadwick using this following equation. 4Be9 plus 2He4 gives rise to 6C12 plus 0 and 1. Another important property of neutron is it is heavier than electron and proton. So that means among the fundamental particles or subatomic particles, neutron is having higher mass than the remaining two. That means electron and proton. Isolated neutron is unstable and it disintegrates as follows. So that means we cannot isolate a single neutron. This electron and proton are also not isolated. But this neutron will disintegrate into 0 and 1 gives rise to minus 1 E0 plus 1 P plus radiation. So this is the radiation, and minus 1 E0 is the electron. Mass of the neutron is 1.674 into 10 power minus 27 kg, or suppose if it is expressed in AMU, it is 1.0086 AMU, and the density of the neutron is 1.5 into 10 power 14 grams per cc. So far we have discussed about these subatomic particles, that is electron, proton and neutron, their discovery and properties. Let us summarize these properties and values of these fundamental particles. So here these values are represented in the following table. Look at the following table. Here the first column represents the fundamental particle, second one the scientist who discovered this particle, and the symbol charge, which is expressed in absolute as well as relative, and the last column indicates the mass. The first fundamental particle is the electron, which was discovered by Jj Thomson, and it is designated as E, and we have find out the charge of the electron as which is the correct value. Later experiments shows that this value is the correct one, which is approximately taken as minus 1.6 into 10 power minus 19 coulombs. And if you consider the relative charge, while speaking about the relative charge with respect to proton or other particles which are having a negative charge, so therefore the relative charge is minus 1. The mass of the electron is 9.1 into 10 power minus 28 grams. Coming to the another fundamental particle, proton. This was discovered by Goldstein, and the symbol is P. The charge is, which is just opposite to the charge of the electron. So therefore plus 1.602 into 10 power minus 19 coulombs, and a relative charge of plus 1, and mass 1.672 into 10 power minus 24 grams. Neutron. This was discovered by Chadwick, and the symbol is N. The absolute charge is 0. These neutrons are chargeless species. They are not having any charge. And coming to the relative charge, it is also 0. And coming to the mass, it is 1.674 into 10 power minus 24 grams. So therefore, from this table, what is our conclusions? So look at this mass. The mass from electron, proton, neutron. As we move from electron to neutron, the mass of the particle is increases. So that means among the fundamental particles, the massive particle is neutron. Look at this value, 1.674 into 10 power minus 24 grams. So that means which is quite a high value than the remaining particles. And now coming to the electron, which is having the mass of the electron is 1 by 1837 times the mass of the proton. And coming to the charge, neutrons are chargeless species, electron and proton, these two are having same charge but with opposite sign. So this is about the subatomic particles. We go to the another important aspect of these atoms, that is atomic number and mass number. The atomic number, the number of protons present in the nucleus of an atom is called its atomic number, and it is generally denoted by the letter Z. And here the mass number is the total number of protons and neutrons present in the nucleus of an atom is called mass number and is denoted by the letter A. So therefore, from this analogy, the atomic number is denoted by Z itself indicates the number of electrons or number of protons, whereas the mass number indicates the sum of the protons and neutrons. So therefore, the number of neutrons is obtained by subtracting the atomic number from the mass number. So therefore, the number of neutrons is equal to A minus Z. So this can be explained with the help of following. For example, if you consider a fluorine atom, this atom has an atomic number 9 and mass number 19. Here Z is equal to 9 and A is equal to 19. So therefore, from our previous discussion, the number of electrons is equal to 9 because the fluorine is having atomic number 9. So therefore, it contains 9 electrons or 9 protons. The number of electrons is called the atomic number. So therefore, it contains 9 electrons. The number of protons, which is equal to 9. Coming to the number of neutrons, which is equal to 19 minus 9, which is equal to 10. So therefore, the fluorine atom contains the fundamental particles. The electrons are 9, protons are 9 and the neutrons are 10 in numbers. So like this, different elements or the different atoms contains different fundamental particles. Like this, difference is there for different atoms. Another important aspect of this atomic structure is isotopes and isobars. So this isotopes and isobars are particularly related to the atoms. Let us know about this isotopes and isobars. Atoms with identical atomic number but different mass numbers are known as isotopes. So this is the definition of isotopes. Atoms having identical atomic number but different mass number. Coming to this isotopes, isotopes exhibit similar properties. These isotopes, different isotopes are having the same properties. Now, coming to the examples of these isotopes, say for example hydrogen. The isotopes of hydrogen are, hydrogen exhibit 3 types of isotopes. They are protium, deuterium, tritium. So here the protium is symbolized as 1H1. The deuterium is symbolized as 1H2 or it is also designated as D2. Third one is the tritium. It is 1H3 which is also designated as 1T3. These are the 3 important isotopes of hydrogen. And now coming to the another example, that is chlorine. The isotopes of chlorine are 17Cl35 and 17Cl37. Dear students, you remember here at the bottom we represent one number and at the top we represent another number. So you know the significance of these two. Here this number indicates the atomic number, whereas the middle one is the symbol of the element or the atom, whereas the top represents the mass number of the particular isotope. So that means this is the specific notation for any isotope. Among the isotopes of hydrogen, protium is the most abundant. The abundance is 99.985%. So that means when you consider an atom of hydrogen, most of the atoms contains this particular isotope, that is protium. This contains 1 proton and 0 neutrons because the atomic number is 1. So therefore it contains 1 electron and mass number is also 1. So for knowing the number of neutrons, you subtract the atomic number from the mass number. So therefore it is 1 minus 1 is equal to 0. So therefore it contains 0 number of neutrons. That is, no neutrons are present in protium.